Hello and welcome back to the Science of Concrete Materials class. This is lecture number 41 of the class, and we will continue our discussion on the durability module. We have one remaining topic to cover, which is the freeze-thaw cycles. Okay, as we know, porous materials containing moisture are susceptible to damage under repeated cycles of freezing and thawing, or otherwise referred to as frost attack. The hardened cement paste, which has a high porosity, is particularly susceptible to such conditions, and concrete may be destroyed in a single winter in the northern climates, like in the North US and Canada. Fortunately, as discussed in a previous module, air entrainment has proven to be an effective and reliable means of protecting concrete from frost attack. So it is of interest to examine the mechanism by which damage occurs on repeated freezing and thawing, and thereby determine critical factors affecting frost resistance and the reasons why air entrainment is really effective. So when saturated concrete is cooled below 0 degrees Celsius, immediate freezing of the water in the cement paste does not occur. As you know, it must be remembered that the paste contains a wide spectrum of pore sizes, and it can be shown thermodynamically that water in capillary pores will not freeze until the temperature is lowered below zero by an amount depends on the diameter of the pore, or more accurately on the diameter of the neck of the pore. For example, water in pores of 10 nanometer diameter will not freeze until 5 below 0 Celsius or 23 Fahrenheit. And in the pores of 3.5 nanometers, water will not freeze until 20 below 0 Celsius or minus 4 Fahrenheit. So also the presence of alkalis in pore water may result in a decrease in the freezing temperature on the order of another maybe 1 degree Celsius, okay? So even when the freezing temperature is reached, a significant portion of the water in concrete will supercool rather than freeze. Since a seed or a nucleus, ice crystal, is required to initiate the formation of ice. The seeds will form on the exterior of the concrete and in large voids within the concrete, penetrating into the body of the cement paste as the temperature drops. The crystals do not easily penetrate small capillary pores, and can do so only when the temperature drops well below 0 Celsius. Finally, the water absorbed on the surfaces of the calcium silicate hydrate, which forms on the surfaces of the capillary pores, will never freeze, although it may migrate to the capillary pores where the ice has formed. It has been shown that in an unprotected paste, severe dilation accompanies the freezing, which leads to internal tensile stresses and cracking. In air-entrained paste, very little dilation occurs, and actually considerable shrinkage during freezing is observed at low temperatures. We will see why coming up. Okay, so let's look really at the mechanism of the frost action. What happens? Several different processes can contribute to paste behavior during freezing. These are the generation of hydraulic pressure by ice formation, the generation of osmotic pressure due to the increase in the solute concentration in the pore water adjacent to the freezing site, desorption of water from the calcium silicate hydrate, and also the segregation of ice. As we know a 9% volume increase occurs as water turns into ice. But this change is really insufficient to account for all the dilation observed in cement paste and in concrete. Some of the dilation that occurs on first freezing is probably due to direct expansion of ice in microcracks. And this will, increase if progressive microcracking occurs during continued freezing and thawing also. However, the major dilation that occurs must be attributed to other processes within the cement paste. So let us take a look at these processes. For many years, the major contributor to dilation was believed to be hydraulic pressure, as was proposed by T.C. Powers. He explained that as ice forms in a capillary, the accompanying volume increase causes the residual water to be compressed, and this pressure can only be relieved if the water can escape from the capillary to a free space by diffusing through unfrozen pores. However, if the water has too far to move to an escape boundary, the capillary will tend to dilate and the surrounding material will come under stress, eventually causing a tensile failure. As the temperature is progressively lowered, more capillary water is involved in freezing, increasing the hydraulic pressure, and thereby increasing microcracking and dilation. After that, it was actually demonstrated that hydraulic pressure could not really be the major source of damage. As it was observed that when, listen to this, partially dry, non-air entrained paste is frozen, it first shrinks and then expands. Even if initially dry enough to provide an empty pore volume great enough, to accept that 9% increase in volume. The expansion continues indefinitely, even if the temperature is held constant, while under the same conditions. Air-entrained cement paste shrinks indefinitely. Also, freezing damage is observed with liquids that do not expand upon freezing. Okay? So these observations indicate that the water is moving towards rather than away from the freezing sites. Okay, so that there are two possible explanations for this behavior. First, pore ice nucleates from the pore solution, resulting in a steadily increasing concentration of solute in the liquid adjacent to the freezing sites. This higher concentration will spontaneously draw water from the more dilute pore solution in the surrounding unfrozen paste through the process of osmosis. Therefore, once ice begins to form, the movement of water creates an osmotic pressure that can eventually cause the surrounding paste to crack. So this is the first explanation. The second is the chemical potential of water in the form of ice is lower than that of the supercooled water in unfrozen pores and is manifested as, a lower vapor pressure. As a result, the effective relative humidity in the freezing sites is lowered, and there will be a spontaneous movement of water towards the freezing sites to maintain equilibrium. So the process can be viewed as a spontaneous desorption of water from calcium silicate hydrate, which causes the paste away from the freezing sites to shrink, even as significant dilation occurs at the freezing sites. Okay, so that's an explanation for the shrinkage that occurs, as I mentioned in the previous slide. So both osmotic pressure and the differential in vapor pressure have similar effect. Okay, so these are the explanations besides the hydraulic pressure. Also, the buildup of ice in particular parts of a structure on a macro scale may aggravate frost damage in concrete, although it is not the basic cause. Okay, so the formation of ice lenses, as you know, this phenomenon is called, occurs, if you might know, as you know, in soils, and it is responsible for the frost heave in soils. So the development of ice lenses in concrete requires the presence of large voids, which could be micro cracks or voids occurring under, you know, reinforcement, or large aggregate particles, you know, due to segregation or poor compaction. So an external supply of water that can readily migrate to these voids is also needed in this case. Okay, so these are the possible explanation that could be the reason why, or rather the cause of why the pressure develops and cracking occurs due to freezing. Okay, in saturated non-air entrained paste, free space is available on the exterior of the specimen, and you know, a relatively small number of widely spaced air voids, you know, incidentally occurring within the paste or the concrete. So the capillaries in this case serve as the principal freezing sites, with the result that the cement paste will be severely damaged upon freezing. On the other hand, the inclusion of entrained air provides empty space within the paste to which the excess water can move and freeze without damage. The air bubbles have much larger volumes, as we have explained before, than the capillaries within the cement paste, and therefore any water in the air bubbles will begin to freeze at a temperature close to zero. So the air bubbles are mostly empty, but may have a film of solution on their surfaces, and it is, you know, thick enough to freeze. So the formation of ice in the air bubbles then allows the processes of osmosis and desorption, I just explained just now, you know, reducing the level of saturation in the adjacent cement paste, to proceed harmlessly. So the bubbles basically act as safety valves, drawing water from the cement paste and serving as a reservoir for both ice and concentrated pore solution. Okay, so this is really the power of providing entrained air bubbles within the cement paste or within the concrete, where the frost attack is a potential. Okay, so let's look at this figure, what I just was saying about the ice formation in the pore. In the absence of this void or air voids we are providing, the pressure will build, you know, within the pores, because the water, depending how much voids are available, if we do not intentionally add them, the water may the ice may end up, you know, forming within the pores, and also will result in dilation and cracking. Okay, so this is the mechanism of what happens when we provide air voids, which are basically the safety valves that will prevent damage due to freezing. And this is, you know, an SEM micrograph. Actually, it's taken for a cement paste sample, and it shows, here is this, you know, a section on a air voids, and it shows you the movement of the moisture and the formation of the ice. Okay, so it's really a very powerful technique, you know, adding the air entrainment to prevent the frost damage. So we spoke about, you know, the air entrainment during the lectures on the chemical admixtures, if you recall, and we talk about something called the spacing factor, you know, how closely and how frequently we need to provide these air voids in order to have an optimum performance. So the spacing factor, you know, determines the average distance the water must travel to reach the free space. Okay, so we're talking about, you know, all over the place here, the paste, we have to have these voids close enough so the water does not travel far enough and eventually will cause damage before reaching these voids. Okay, so this distance must not be too great if osmotic pressure is to be relieved. Okay, we need to relieve the pressure before it develops. So hence the requirement for what we call the critical spacing factor. Upon thawing, the water in the air bubbles returns to the cement paste because of the higher surface tension in the smaller capillary pores. In this way, cement paste will not suffer freeze-thaw damage as long as the moisture content remains constant. That's something else to remember. Even poorly air-entrained concrete will eventually be damaged if it becomes fully saturated with the air bubbles filled with water. So that's another factor. The moisture plays a role here that we have to be aware of. Okay, so based on the mechanisms described, it can be shown that the resistance to freezing and thawing depends on permeability. So the degree of saturation also of the paste and the amount of freezable water and the rate of freezing, okay? In addition to the average maximum distance from any point in the paste to a free space or a free surface where ice can form safely, okay? So these are really the factors that affect or influence freezing and thawing damage. Partially dry concrete will not suffer freeze-thaw damage because the larger capillaries are empty and provide the necessary free space throughout the paste. Air entrainment is required for protection only for concrete that is frozen in near saturated conditions. Okay, so the entrained air bubbles do not readily fill with water except when the concrete is immersed for long periods of time. So once the air bubbles are filled with water, however, the concrete has a greater amount of freezable water and will become highly susceptible to frost damage. Okay, so the presence of moisture is of great importance here. We have to be careful about that. Okay, so we looked at what happened during freezing and how the damage or the possible explanations for the damage, how the provision of air bubbles or air voids intentionally added will serve as safety valves to relieve the pressure that will develop once the temperature drop to a certain level where the water in the pores starts to freeze. And we have now looked at what are the factors that influence the freeze-thaw damage, and of course in order for us to control them and mitigate them in order to prevent damage. So let's look at what are the available tests to assess the potential for freeze-thaw damage. A number of different tests have been developed, to assess the long-term frost resistance of concrete. These involve subjecting concrete to different freeze-thaw cycles and then measuring the progressive internal damage by monitoring weight loss, length change or dilation, okay, and the decrease in strength, or other way to measure it is the decrease in dynamic modulus of elasticity. The tests differ in the nature of the freeze-thaw cycle used and the condition of the specimen during the test, but all tests are arbitrary since they involve only one set of conditions, okay? As we have seen, the potential for frost damage depends on the freezing rate, water cement ratio, time of moist curing, degree of saturation, and these may vary widely in actual surface conditions. In actual surface conditions, these factors will vary a great deal. So predictions from freeze-thaw tests are not always a good indication of actual service performance, and results should be treated with caution. Okay, the results of the tests are not always accurate, universally accurate. There has to be sound judgment from an experienced professional to make these interpretations. Okay, the standard method, test for the method of test, the standard method of test described in ASTM C666. This prescribes a cooling and heating cycle between 4.4 and minus 17.8 degrees Celsius, between 40 and 0 Fahrenheit, to be completed in 2 to 5 hours. Okay, so freezing can be done while the specimen is immersed in water. This is according to procedure A of the standard, or in air according to procedure B, because we have two different procedures prescribed in that standard. But in both cases, it is thawed in water. So the test requires that not less than 25% and 20% of the cycle time be used for thawing, in procedure A and B respectively. 25% for procedure A, 20% for procedure B. The test is continued, either continuously or intermittently for 300 cycles, or until the dynamic modulus has reached 60% of its initial value, whichever occurs first. Then, based on that, a durability factor is calculated according to this equation. P times N over 300. P is the percentage of initial dynamic modulus, and N is the number of cycles. Okay? There are no definite values for durability factor for acceptance or rejection of the concrete subjected to this test. Using procedure A, value of less than 40 suggests that the concrete may be unsatisfactory, whereas above 60 is likely to perform well. But there is no guarantee that this prediction will hold true. And again, we said, the conditions vary immensely from in the field, from what the conditions are subjected to and during the test. Okay, both procedures A and B are used by various agencies to evaluate the durability of coarse aggregate, as well as the durability of concrete mixtures as a whole. So that's another thing. Procedure A is really especially severe since most specimens eventually become fully saturated and eventually fail. So even concretes that perform well in the field may perform poorly when subjected to cycles of freezing and thawing in water. And again, replicating the conditions and being accurate in our predictions of the service conditions of the concrete in order to run the test. Otherwise, the test will not be representative of what will happen, or vice versa. So the major objection really to ASTM C666 is the unrealistically high rate of freezing, since in the field rates exceeding 3 degrees Celsius per hour are rarely encountered. So ASTM C671 overcomes this objection by specifying one freeze-thaw cycle every 2 weeks. Employing this rate of freezing with a rapid thawing regime. So damage is monitored by measuring linear expansion during the test, which is, continued until critical dilation, meaning, until dilation begins to increase sharply, or a desired number of cycles is completed. This test allows the user to specify the curing history of the specimen and the exposure conditions to most nearly match the expected service conditions. So that's the difference between this test and the ASTM C666. And again, using this test and really interpreting the results should be done by a professional who can really call the parameters and make sure whatever test is being performed and the result are applicable or can be implemented to the prediction of what will happen in the field. Okay, so by this really I will come to the end of this lecture, and also this will be the end of the durability module number 8 of the class. And by this also we have finished the class, which is the science of concrete materials class we started a while ago. So this is lecture number 41, is the last lecture of the class. I hope really I have contributed some to the knowledge of at least some of you regarding the science of concrete materials and concrete technology in general. I hope if you have any questions, comments, inquiries, do not hesitate, please, to drop me a comment, send me an email, whatever you prefer. I'm thinking about also making a few more lectures about special topics that I really intentionally did not want to make a part of this class, and I said I will cover them later, like high strength concrete, field practices, and maybe some other special topics, depending, you know, how much time I have available to do it. And again, I thank you for watching, and I hope I will hear from you. Thank you, and I will see you in another class. Thanks.